Round robin is one of the oldest and easiest preemptive scheduling algorithms which is often used in interactive systems. Quantum and ready queue are important terms to know when talking about the scheduling technique. The quantum or time slice is the period of time for which a process is allowed to run on a CPU in a preemptive multitasking system. The ready queue consists of all processes in the state ready, so they are eager to get the CPU. How does the round robin algorithm basically work? All processes in the ready state are located in a queue, the so-called ready queue. The quantum is assigned to each process. The first process in the ready queue obtains the CPU for the duration of the quantum. While the process is running on the CPU, its process state is running. If the process is still active after the quantum has been depleted, which means the process still has work to do, and at least one process is waiting in the ready queue, it will be preempted, set into the ready state, and inserted at the end of the ready queue. After that, the next process in the ready queue gets the CPU. A blocked process which switches into the ready state will be inserted at the end of the ready queue. So let's do a little example. Given the system with the following processes: process P1 with the arrival time of 0 milliseconds and a CPU burst of 100 milliseconds. The CPU burst is the time needed to complete a task. Process P2 with the arrival at 10 milliseconds and a CPU burst of 40 milliseconds. Process P3 with the arrival time at 20 milliseconds and a CPU burst of 50 milliseconds. And finally process P4 with the arrival time at 30 milliseconds and a CPU burst of 30 milliseconds. The scheduler of this system uses the round-robin scheduling algorithm with a quantum of 30 milliseconds, which means a process can run up until 30 milliseconds without interruption. At the beginning, the ready queue only consists of P1. This process is directly assigned to the CPU and can use up its quantum of 30 milliseconds completely. After 10 milliseconds, process P2 arrives in the ready queue. After another 10 milliseconds, process P3 arrives. 30 milliseconds after process P1 started his work, process P4 arrives. After P1 depleted its quantum, it switches into the ready state and is inserted at the end of the ready queue. After that, P2 gets the CPU and uses up its whole quantum. But the process is not done yet. Therefore, it switches into the ready state and is inserted at the end of the ready queue. P3 runs for 30 milliseconds and still needs to run 20 milliseconds afterwards. P4 runs for 30 milliseconds and completes its task. The process is terminated and not sent back to the ready queue. P1 is the first process in the ready queue again and runs for 30 milliseconds on the CPU, but it still needs to run 40 milliseconds afterwards. Nevertheless, the dispatcher sends P1 back to the ready queue. Shortly after that, P2 gets the chance to complete its task. It doesn't even need the whole quantum of 30 milliseconds, but only 33% of it, namely 10 milliseconds. Now P3 starts working again. It also uses only 2/3 of its quantum and terminates. Now P1 is the only process in the ready queue. It gets the CPU directly and can use up its whole quantum. After P1 depleted its quantum, it is not preempted and sent back to the ready queue, since no process is waiting there. So P1 can work 10 more milliseconds until the job is done. The choice of the quantum determines the success of this scheduling strategy. If the time slice is too long, processes will take longer to respond to input, which is disadvantageous for I/O processes. If the time slice is too short, then the scheduler will consume too much processing time caused by the overhead of a context switch. A lot of performance issues can be solved by throwing hardware at the problem. This could also be a solution for scheduling strategies spread over multiple CPUs. But just defining a larger quantum does not necessarily help. A typical quantum for round-robin lies between 10 milliseconds and 100 milliseconds. Round-robin schedule is unfair for I/O processes since they can only use up a fraction of their quantum, and they have to wait for the end of CPU-intensive processes. As a solution, the virtual round-robin algorithm has been developed where unused quantums are recorded as a time credit. Thanks for watching. If there are any questions left, please leave them in the comments.